Alan, thank you so much for being here. Very excited to hear about Rescue Prime. And with that, I'll let you take it away.
All right, thanks for the fabulous introduction. I did notice, though, that you didn't brave to pronounce my surname. Probably a very wise choice.
Discretion is the better part of valor, as they say, Alan.
Exactly, exactly. For those who wonder how it is pronounced, I say Szepieniec, but then someone who's actually from Poland might disagree about the correct pronunciation. So there you go. This is obviously joint work with Tomer Ashur and Simon Doge. And well, this is a presentation about a paper called Rescue Prime, and there's some other stuff in the title of that paper. But I'll also be talking about the original paper, which I'll refer to as the Marvellous paper, which Rescue Prime is based off of. So here's a quick outline. First, I'll be motivating why we need arithmetization-oriented hash functions, and then I'll look at what Rescue and Rescue Prime do and how the two differ. And then I'll cover the security argument against algebraic attacks briefly, and lastly, I'll have a conclusion. So my slides are probably roughly 30 minutes in terms of presentation time, and if you have any questions, please raise your hand, join in, or if you're shy, you can also write it in the chat and Alex will read your question, but I certainly prefer an interactive dialogue to a standalone lecture. So in the context of zero-knowledge proofs, there's always this transformation going on where you start from a computation at the top and it's turned into two programs at the bottom, a prover and a verifier, such that the verifier does not need to have the resources that performing the computation naively would require. So the prover, which performs the computation, but in addition to performing the computation, produces a proof. The prover has access to secret inputs. And that's when we have a zero-knowledge proof system. Or sometimes instead of secret inputs, it has access to much more running time. And then we have a succinct verifier proof system. And in fact, you can combine the two. And the whole point is that the verifier does not need to have access to those resources, but instead has access to a proof pi. And based on the construction of that proof, the verifier decides whether or not the claim is accepted as true or not. Most of the research in proof systems is about this compilation process, and that's where all the moon math is going into, and that's where all the information theoretic analysis is going into, and there is no shortage of papers and results dealing with that block. But that's not what this presentation is about, or what the paper that this presentation is about is about. We take a step up and have a look at the computation itself. And in particular, oftentimes you need to evaluate a hash function in that computation. And since you're going to transform this entire computation into a prover and a verifier, the hash function can affect the performance of that prover and verifier very, very strongly. If your hash function is rather naive, then you'll have a very expensive prover and verifier. And if it's geared to optimize this transformation, then maybe that cost is much less. So that's the idea behind Poseidon and Rescue, and by no means is that list exhaustive. There are a few others as well. And so Rescue is one of these hash functions that already exists that is very amenable to transformation by a zero-knowledge proof system. what we're introducing in this paper is rescue prime, which is almost basically 99% the same thing. It's just presented in a different way, and there are a couple of minor tweaks that make it even more amenable to transformation by a proof system. So here's a slide that I drew from one of the reports by Starkware, where they consider various hash functions to build one of their applications on top of. I think the hash functions go into a Merkle tree, or it's a VDF where you evaluate the same hash function many times. And they compiled some cost metrics, and with respect to SHA-2 and SHA-3, you're in a completely different ballpark with respect to this cost metrics than if you look at the arithmetization-oriented hash functions. And then, in fact, even among the arithmetization-oriented hash function, rescue is already inching out ahead of its competition, but then rescue prime is even better still. So I don't know exactly what the number would be, but I expect it to be 2.9 or something. So it goes to show that arithmetization-oriented hash functions are useful and are being used in practice. So that's why we designed them, or designed one family of them in the past. So this is the original paper, which I will refer to as the Marvellous paper. And this paper didn't just introduce the hash functions vision and rescue. It also introduced design principles for designing secure ciphers and assessing their security. As a result of introducing design principles and this elaborate security assessment, the paper is rather difficult to process, particularly for implementers who just want a list of instructions because they want to know what to do. They don't care about the exact complexity of an algebraic attack. So that's why we have the second paper. I should probably say the motivation for the second paper is because the first one was finally accepted after, I think, 5 submission attempts. But now that it is finally accepted and more or less Hello?
Hey, Alan, sorry, there's a question in the chat. I'm just going to read to you if you don't mind.
Go ahead.
So question, I noticed that many are using 60, and I'm referring to the slide note of the results of the different functions. I said, I noticed 61-bit prime fields, which is obviously much smaller than traditional hash functions. Is there any issues with collision resistance? And I was thinking you were asking just in general, are there any special assumptions that you need to make about this class of hash functions versus something like SHA-256? So it's 2 questions in there for you.
Right. So while these hash functions are defined over 61-bit prime fields, the output of these hash functions are going to be multiple field elements. So in the end, you'll have 122 bits of output, or even 244 bits of output, depending on how many field elements it outputs.
Got it. And Dara also in the chat said the output of the hash is larger than the field in that case, which I think is what you just said.
Exactly. Correct.
Thank you. I'll chime in if I see questions.
Good. Yeah. So this paper, the goal here is to take just one aspect, one hash function of the two hash function families that we specified in the previous one, and make it as simple as possible and make the instructions for implementers as clear as possible. And while we were at it, we decided to apply some simplifications. But those are really not very, very meaningful. So the scientific novelty of this paper is basically zero. So I'm sorry to disappoint anyone who was coming to this lecture for seeing the scientific novelty, because if you already know how rescue works and what the argument for security is, this will just be a repetition of all that knowledge. On the other hand, this paper does have what I still think qualifies as scientific contributions, namely, we have an easy specification of the hash function, or easy to follow rather. The specification itself serves as a standard, so that if you implement what's described in this paper and someone else also implements it in a different code base, in a different language even, at least it will be the same hash function that's being implemented. And thirdly, it is slightly simpler than rescue. So I'll get into that later.
And
so what is the
just another question here? And by the way, so everyone knows in the chat, and Alan also so you, the slight delay between folks who are watching and what you and I are discussing. There's like a little bit of a lag, so some of the questions are going to be coming like a little delayed from your talk. But there's a question from Thor in the chat about returning to this around collision resistance and the output of the hash function. And the question is the hash function objective? That is, even may be larger than the input field, wouldn't the number of possible outputs be limited to, he says, 2 to the 61?
Hang on. The output field and the input field, that distinction doesn't make much sense. The field is how you define the plus and times operations, right? In both cases, you take plus modulo p and times modulo p, and you build your hash functions out of plus and times alone, no other operations allowed. The output of this function that you built are going to be several numbers modulo p. So that's what we refer to as field elements, is a number modulo p.
Okay, and I've got a thumbs up on the chat. So thanks for that.
All right. So what's the difference between rescue and rescue prime? Well, for starters, we flip the order of the S boxes, and I have a slide motivating just that. We simplify the derivation of round constants, and if you were confused about how the round constants were derived in the original Marvellous paper, it doesn't really matter that much, but this go around, at least we have a easy specification, so it's difficult to get this wrong. And thirdly is the security margin is reduced. So originally, we set the number of rounds to be 2 times the number of rounds that we know can be attacked by, that we expect can be attacked by the best performing attack, just to exaggerate on the conservative side of things. Now that was almost 2 years ago when we set that security margin, and in the meantime there has been some analysis of arithmetization-oriented hash functions, but the security of rescue is untainted. The efforts in breaking rescue have gone essentially nowhere, as far as we know. So we expect it's safe to reduce the security margin from 100% to 50%.
And Alan, 2 more questions in the chat. Sorry, I guess we asked for this. So question from Dara, it matters. Oh, and by the way, if anyone, I butcher your name, I'm going to apologize. DM me and tell me that I'm butchering it, and I'll figure something else out. So question is, it matters about the security analysis, this family of habits. It matters that the round constants are super random, right? Otherwise, there is a backdoor possibility. So that's one question from Daryl. I'll let you tackle that one first.
There are a couple of functions that the round constants serve. The first and foremost thing is that they make every round into a different function. If every round is the same function, then a clever attacker can trick the cipher into recomputing parts of itself, and there's this slide attack and all sorts of self-similarity attacks are possible if rounds are not distinct from each other. So the first and foremost purpose of round constants is to make every round unique. In traditional ciphers, it is often possible to choose malicious round constants. These would be specific numbers that were designed to enable certain linear or differential properties. And if you don't know why those numbers were chosen, you have no hope in discovering those linear or differential properties. Whereas if you do know why those numbers were chosen, then you have a leg up on anyone else who's trying to attack it. So that's one of the reasons why people distrust DES and triple DES as well, in fact, is because the specification just gives you the round constants, but it doesn't tell you where they came from. And as a result, if you're sufficiently paranoid or even mildly paranoid, you probably shouldn't trust DES because someone somewhere might be sitting on a way to attack it that hasn't been discovered. So the second purpose of round constants, and rather the purpose of generating round constants as the result of a pseudo-random number generator, is to convince everyone that we don't have anything hidden up our sleeves. We didn't choose these constants to satisfy particular algebraic properties.
Got it. And another question from Sean in the chat. Is there a difference between the base prime and the corresponding order? And he clarifies the order is 61, not prime, question mark.
So the base prime defines a field, and the field in discrete algebra, the order refers to the number of elements of the field, but that's in particular circumstances. Sometimes you say the order of an element, and then you mean the order of the group that that element generates. And if you take a random element from your field, odds are that the group that it generates is going to be p minus 1. So definitely distinct from the order of the field.
Great. All right, thank you.
I didn't get the clarification. Can you repeat that?
Oh, yeah. So Sean, so again, the full question. So is there a difference between base prime and corresponding order? And then the follow-up was order is 2 to 61, not prime, question mark. So I think, yeah.
Yeah, so you could, I don't know if 2 to the 61 plus 1 is prime, but it's certainly possible that there is a prime of a similar form where the order of the multiplicative group is 2 to the k, where k is sufficiently large. In fact, those are good primes to use in transparent proof systems using Fry, which is what Stark uses, for instance.
Great. Well, let's move on, Alan, and I'll let you know if there's any more questions in here.
All right. So that was the introduction. Drinking break. Let's see, construction. So in the original Marvellous paper, we specified rescue as a result of several steps, and hats off to anyone who managed to take those steps with us, who was with us the entire way, because it's actually a rather long and winding road. So first we specified the block cipher, and then when you set the key to 0, then you get a standalone permutation, and when you instantiate the sponge construction with this permutation, then you get a sponge function whose output is infinite, but if you truncate this infinite length output to a given length, that's how you get the rescue hash function. So this also shows how to get the round constants for the rescue hash function, right? Because we specify the round constants for the rescue block cipher. And then you set the key to 0. This gives you essentially new round constants for the permutation, because there is also a key schedule involved in the block cipher, which transforms the constants. But in the end, that doesn't matter. The exact derivation of the round constants doesn't matter too much, as long as it is as it makes sure that every round is different, and that it's clear that it's difficult to choose round constants with particular properties. So this was rescue, and then for rescue prime, we really only specify 2 things: rescue xlix and rescue prime. So rescue prime is the hash function, and rescue xlix is the permutation. And we don't even specify what the sponge construction would look like. I mean, it's obvious if you know what a sponge construction does, but we omit any reference of that, and we go straight to a truncated sponge construction. Not sure why that's happening. All right, there should be a note here about the correct pronunciation of rescue xlix. My co-authors insisted on using English script to denote the correct pronunciation of xlix, but I find it confusing because the symbols happen to match exactly with the word 49. There you go. So I already mentioned that hang on, there's a slide missing here. Let me quickly try to recompile my slides, and I'll see, and I'll make sure that it's there. Hang on, how do I stop sharing my screen? Here we go. Feel free to ask me some questions in the meantime, if there are any. Recompiling shouldn't take so long.
We'll give it a second here. I think there's going to be like a 10 or 15 second lag, so we'll probably hear questions here in a few seconds while you recompile.
Sorry for the technical hiccup. I should have made sure that my slides made sense.
So we have one question that just came through. Why truncated sponge in
the sponge function outputs infinitely many field elements. And it's kind of difficult to work with infinitely many field elements in practice. It's kind of difficult to work with infinitely many field elements in practice, so you're going to have to truncate it regardless. and so you might as well define the truncation in the
Got it. And then
All
question, what are the material differences between a Stark friendly hash function and a Snark friendly hash function? Is rescue prime one of the former?
That's a great question. Stark friendly hash function is a hash function that gives rise to a very small arithmetic intermediate representation, which is the cost metric for the Stark proof system. The way you achieve a very small error is by using only a small number of additions and multiplications. Now, the Stark proof system is not the only Snark proof system in existence. There are also pairing-based Snarks and even Snarks based on groups of unknown order and plenty of constructions out there. And very few of them actually use arithmetic intermediate representation error. Most of them actually use arithmetic circuits and R1CS or even Hadamard relation. These are different representations compared to error of a computation. And as a result, the complexity metric will be different. However, the complexity metric is also very small when you're using a small number of additions and multiplications. I think for R1CS, the number of additions doesn't matter that much, but the number of multiplications is key. So it highlights that R1CS complexity is different from error complexity. But still, a hash function that's going to be efficient for Starks is also going to be efficient for R1CS, despite the minor dissimilarities in the complexity metric. All right. In the meantime, I recompiled my slides so we can go back to present. All right. Yeah, so my co-authors wanted to introduce this Anglo-Saxon phonetic notation, whereas I prefer the international phonetic alphabet way to write xlix. So the round function of rescue was defined by 6 layers operating on a state of m elements. And we discovered early on that m has to be 2 or larger, because if it's not, then the degree of regularity grows very slowly, and that's a bad thing from the point of view of defending against algebraic attacks. But if you choose m equal to 2 or larger, it should be fine. So in the first layer, we apply the S box, what's called the S box, to every element individually. And what this S box does is it sends x to the power 1 over alpha. Alpha here is the smallest exponent co-prime to the order. Now, when I say order here, I mean order of the multiplicative group, not the order of the field. So the order of the multiplicative group is p minus 1, because we're working over prime field. And most of the time, alpha is going to be 3. If 3 doesn't work, then you choose alpha to be 5. If 5 doesn't work either, then you choose alpha to be 7, and so on. If possible, pick a prime field such that alpha equals to 3 works. So in particular, the fourth layer, which is once again S boxes, that's just regular raising to the power alpha, and alpha is 3. So you should think of this first layer of S boxes as the inverse of the fourth layer. All right, then in the second layer, we have a multiplication by an MDS matrix. This is just, MDS is a term borrowed from coding theory, and it guarantees that your matrix has good properties from the point of view of studying the propagation of differential patterns and linear dependencies. It makes the analysis, the security analysis, a lot easier if the matrix is MDS. Over large fields, as we define rescue, most matrices are MDS matrices, but nevertheless, we give a concrete standard specification how to find this matrix, both in rescue and rescue prime. So then the third layer consists of injecting the round constants. Rescue specifies the block cipher. So these are not the round constants, but these are the subkeys. Where do you get the subkeys from? Well, you get them from the key schedule, which is not shown in this figure. So anyhow, injecting, you just add, for every wire, there is going to be a subkey, and you just add the subkey to that wire. And then the same process repeats, except the S boxes are the inverse of what they were at the start. You raise every element to the power alpha, and then you apply the MDS matrix, and then you inject the next sequence of subkeys. For rescue prime, we flip the order of the S boxes. So first we raise to the power alpha, and then we raise to the power 1 over alpha. And since there is no key schedule to be seen anywhere, the constants that you're injecting here are actually the round constants of the hash function. So it's almost the same thing, but not quite. Why are we flipping the order of the S boxes, and doesn't this come with a security hazard? We think not. So if you visualize one execution trace of the permutation, and if you look at where you would insert new variables when you start to model this as a sequence of permutations, what you would do is you would, at the very start, you would have one variable for every wire. And at the very end, you would have one variable for every wire. But then you would make use of the fact that if you go from the middle of this round to the middle of the next round, you can relate the variables from the middles of two subsequent rounds using only degree alpha equations. We call that folding. And this folding works across the entire permutation, except it doesn't work at the ends. So that's what I've drawn here. The half blocks, let's say, are the full rounds, and then the dotted lines are where you want to specify variables when you model this as a system of polynomials for a algebraic attack. Now, for rescue prime, you want the variables to coincide with the boundaries of the rounds. And for the inner part of the permutation, this coincidence is exact. It matches perfectly. But then there's this odd question: what to do at the ends, at the start and at the end. And well, in the end we decided to just add a single half round at both ends. And so as a result of adding the single half rounds, it can't be less secure because there are more half rounds now than there were previously. And the arithmetization is more regular. In fact, there are the same number of variables and the same number of equations It's just the shape of some equations, namely the equations that capture the ends that are different. So in fact, in some cases, this flip of the order of the S boxes improves the arithmetization, and in other cases, you're as bad or as good off as you were previously. So what does the truncated sponge look like? Well, this is a diagram where you're hashing two blocks. Now, one block consists of R field elements. So R could be 3 or something. And in that case, we're hashing 6 field elements in total. So a sponge consists of a state, and the state consists of R plus C elements. R is the rate, and C is the capacity. And in every iteration of the absorbing phase, we read R many field elements and add them to the top R elements of the state. And then after every read, we apply the xlix permutation. And we do that just as many times as you need in order to absorb the entire input sequence. I should note that there is an issue if you're going to hash variable length inputs. You cannot forget to include a delimiter. But if you know that your inputs are fixed length always, then you can safely omit the delimiter. So that's the absorbing phase. And then in the squeezing phase, for sponges, you can squeeze out an unlimited number of elements. But for rescue prime, which is a hash function, you're only ever allowed to squeeze out R field elements. And that's just reading the top R elements of the state after the absorbing phase is done. All right, so let's have a look at the security argument. And by the way, here there is absolutely no difference between rescue and rescue prime. So the best performing attack, as far as we can tell, is the Grosvenor basis attack. And what I will be describing in this slide is only very crudely a Grosvenor basis attack. In fact, this is more reminiscent of an XL attack, but regardless, it suffices to capture the intuition of where the performance penalty, or rather where the complexity of a Grosvenor basis attack comes from. Because you can always interpret a Grosvenor basis algorithm through the lens of elementary row operations on a Macaulay matrix of degree D. So suppose we have a system of equations which we obtain from modeling the cipher, and that shouldn't be difficult because these ciphers come with the selling point that they should be easy to model as systems of equations, because that's what you get when you build a cipher out of only addition and multiplication. So once you have a system of equations, then you take all the variables that appear in all those equations, and I simplified all those variables to just x and y for the purposes of this picture, but in reality that would be all of them. And you take all monomials of degree at most d. So that's a very big number of monomials for even modest d's. So in my picture, I took degree 3. So that gives x cubed, x squared y, xy squared, and y cubed. Those are the degree 3 monomials. Then we have the degree 2 monomials. Then we have the degree 1 monomials. And then we have the degree 0 monomial. All right, so in this matrix, it is easy to put the original polynomial equations that you start with, because they just give you coefficients that belong to those monomials. So you put those coefficients into their respective position, and now you have a matrix where every row corresponds to an equation and every column corresponds to a monomial. So far, so good. You are allowed to do row operations on this matrix already. However, that's not going to give you any new information because these polynomials are nonlinear. And, well, as a result, you cannot bring them into reduced row echelon form, or rather you can bring them into reduced row echelon form. It's just not going to give you any useful information about the degree 1 monomials from which you can read out the solution. So what you need to do is you need to multiply these polynomials by monomials. Rather than just scalars, you multiply them by monomials. And that means that the new rows in this matrix are going to occupy columns of higher degree as a result of multiplying by monomials. So suppose we have two equations that we start with, then we multiply both equations by x and by y, so then we get 4 new equations. And obviously those numbers generalize to higher numbers. And then once we've populated this matrix, we run linear algebra, for instance, Gauss, and then we get this nice row-reduced echelon form. And if everything went smoothly, we should be able to read out the values of x and y, because they are at the bottom on this diagonal. This diagonal hopefully is 1. So that means that the bottommost 2 elements of this column, this pink column on the right, should give you the values for x and y respectively.
Quick question from Ferdinand in the chat here, and this I think goes back to the discussion of the permutation. Can't the, or sorry, the XLix. Yeah. So okay, correcting me. They're having a discussion in the chat. So there is no. Please continue, but it has a lot of interesting chatter between some folks. So about that, I didn't interrupt the flow, but go ahead, Alan.
All right. So once again, this is a very, very, very crude representation of how Grosvenor basis algorithms work, but nevertheless, it suffices to capture the source of their complexity. Right, of course, step number 4, I already covered that, is you just read out your solution once you have the matrix in this form. So the source of their complexity is bringing this matrix into reduced row echelon form. And we actually understand this problem quite well. What we don't understand quite as well is how big must D be? How big does this matrix have to be before you get this nice diagonal and column vector form out at the end? Because if your D is not big enough, then you're not going to have enough linearly independent rows, and you won't be able to read out your solution. If your D is too big, you will be able to read out solutions, but it's going to be too expensive to get to that point. So D is the big question in this context. And that's where the notion of the degree of regularity comes into play. Crudely phrased, the degree of regularity is how big this matrix needs to be before you can read out a solution. I bet there are a couple of researchers in Paris right now who I've just given a heart attack with that crude phrasing, but I don't think it's that far off from the truth. But if you want to know what the truth really is, here is a formula dump. So the degree of regularity is a property of the ideal, which is the generalization of the vector space. If you take the polynomials you start with as basis vectors, and you allow not just scalar coefficients, but also polynomial coefficients, then you get an ideal and not a vector space. And the ideal spanned by the polynomials that you start with has a degree of regularity. And in the worst case, from the point of view of the attacker, this is a regular sequence of polynomials, and then we actually have a not very closed form expression, but we have a definite expression. Then we know that the degree of regularity is equal to the degree of the first non-positive term in the formal power series expansion of this expression, product of 1 minus z to the power I polynomial's degree over 1 minus z to the power number of variables. It's terrible, but fortunately, if the number of polynomials equals the number of variables, then we get a closed form expression for the degree of regularity known as the Macaulay bound. And this is much easier to work with. But of course, this is still assuming that the system of polynomials that you start with is regular or worst case from the point of view of the attacker. And in practice, we do not observe that those systems are regular. In fact, we observe that the concrete degree of regularity is less than what the Macaulay bound would predict. Unfortunately, the only way to determine what the concrete degree of regularity is, as far as we know, is by running a Grosvenor basis algorithm and looking at what degree was reached. And as a result of that, it's prohibitively expensive to get more data points to justify this linear fit, but there is a closed form expression for the orange line, which matches with all the observed data points. So based on using that closed form expression for the concrete degree of regularity, we can estimate the complexity of a Grosvenor basis attack. And that's actually a surprisingly simple formula, which you see here. And let me annotate this. So dreg is the degree of regularity. And based on this picture, you look at the number of rounds that you're considering, and then you look at the value of the orange line. That's the degree of regularity. And then n is the number of variables. Omega is the linear algebra exponent. So if you're going to use naive Gauss, then it's 3, but if you're going to use fast matrix multiplication like Strassen, it should be 2.8 or something, and if it's even fancier matrix multiplication, you can get down to 2.4. And even if you use sparse linear algebra techniques, well, it's not clear how that would work yet, but we certainly cannot rule out that possibility. So maybe 2 is feasible. So in fact, 2 is the linear algebra exponent that we chose already in the original Marvellous paper. So the reason why there's a combinatorial expression here is because this means the number of monomials of degree at most d. So this is the width of your matrix, and you need at least as many columns. In practice, you can do with slightly less, but as an order of magnitude, you need that many rows in order to triangularize, or in order to get that nice diagonal form as a result of running as a result of bringing the matrix into reduced row echelon form. So based on this expression, you can compute how much work does it take the attacker to compute a pre-image of a hash function that uses n many rounds. And whatever that number was for rescue, we doubled it and said rescue needs that many rounds. But since the mean time has seen essentially no progress towards breaking rescue or undermining its security, we've decided that it's okay to change this factor 2 into a factor 1.5. So still there is a security margin, but it's less extreme than the original security margin that rescue had. So that brings me to the last slide, which is essentially a couple of bullet points. Rescue prime is out, and it's a hash function just like rescue hash. And you can see the specification on Yacker eprint 2020/1143. Of course, we're still not 100% sure about the security. So if you want to have a look at the security, by all means, also feel free to reach out, and I'll be happy to answer your questions both via email and now.
Great. Hey, thanks, Alan. Let's give folks in the chat, feel free and ask any questions that you have. And then, or, you can ask them in the chat there, or I think he's just caveated that he's not a symmetric cryptanalyst, but I think that's going to be followed by a cryptanalytic question. But anyway, for everyone else watching, if you have a question, you can either raise your hand and just click share audio video, and I can call you up, and you can pronounce. I can just call on you and you can ask directly, or just drop it in the chat, and I'll read it aloud. So we'll give folks a couple of minutes.
Well, that chat has really seen the chat has really seen a lot of messages. I was afraid it was going to be a bit of a middle of nowhere kind of tumbleweed experience.
Actually, there's a question for you. Maybe I'll just, rather than verbalize it, I'll just let you read it, Alan. Yeah, that's the first one, and then Dara's got
one. By Bobbin? All right. Can there be arithmetization-friendly functions as efficient outside of snark-starks as regular hash functions? Hang on, I think, I'm not sure I understand the question correctly, but I think what you mean is when evaluated on a CPU, whether the hash function can be as efficient as SHA-2 or Blake. The answer is it's difficult because when you design a non-arithmetization oriented hash function, you get to use bit fiddling, and bit fiddling is really fast, and it can still give you a reasonable security level, whereas arithmetization-oriented hash functions, generally speaking, don't allow bit fiddling. Now, I say generally speaking because if you work over a binary field, then you obviously do have access to XOR, because that's just addition over a binary field. But you definitely don't have access to AND or the majority function or rotations. And those are operations that are really, really, really cheap and make traditional hash functions very fast. Also, generally speaking, in the zero-knowledge proof, you want your soundness to come from the fact that you're using a large field. And if you're going to use a large field, then multiplication is going to be very expensive compared to traditional functions where you can just use field elements. Well, field elements, it's not really a field element anymore because they're using other operations as well, but you can use state elements as small as a byte or even a nibble, and there's no problem with multiplying them if you would want to multiply in the first place. Am I worried that there hasn't been enough time since Rescue was published to be proposing a new specification? Well, it's hardly a new specification because there's a really very, very strong similarity. Although I think the question can be recycled with respect to, aren't we worried about reducing the security margin? Yeah, to a certain degree, but at the same time, you have to dance around and catch attention to be a target, and we certainly want to be a target of cryptanalysis, because the only way that we will get a justified confidence in the security of this function is for cryptanalysts to direct their attention to rescue prime and to fail. And if they should succeed, then we're better off if they succeed in breaking rescue prime sooner rather than later. And with an eye to motivating cryptanalysis, we think it's a good idea to make it appear more vulnerable, perhaps.
Okay, great. So I think that's the end of the questions. And yeah, with that, thank you very much, Alan, for the talk. I did want to quickly plug, since we were talking about chess at the beginning of this session, there's going to be a little virtual after party for those of you who are familiar with gather.town. It's kind of a little virtual world that we can virtually explore. And I'm told there's a virtual chess game in the world that Anna's created. So if anyone wants to try their hand at playing Alan in chess, he's eager to redeem himself after his game this morning. I believe. I don't know. I'm speaking for you now, Alan, but anyway.
I'll be happy to
it's very gracious of you. Alan, thank you very much for the presentation. And I think we all learned quite a bit. And thank you everyone who attended, and look forward to seeing you all throughout the rest of the day and tomorrow.